In our next question, we're going to discuss a better approach for summarizing a data set. This question is called, "Excuse me, I'm having a skewed moment." In this question, we're going to talk about how we can more precisely describe a large data set using summary statistics beyond just the mean, the median, or the mode, looking at things like the variance, the skew, and the kurtosis. And we're going to try and develop an intuitive sense of what these statistics really physically mean. Let's start off. If we take our data set, we can compute things like the mean very easily in NumPy. We can compute the variance. We can compute the standard deviation. We can compute the skew. We can compute the kurtosis if we import from SciPy. And we may have even relied on these before. We say, if we're going to compute a median, we might as well compute the variance and the standard deviation. And there's some implicit meaning behind these. We might rarely reach for things like the skew and the kurtosis. But think about what our value proposition from computing these are, what our motivation is. Our motivation is, can we find not one single scalar value, but a collection of scalar values that describe something interesting and meaningful about this large data set, so we don't have to tell somebody, oh, it's a billion points, point 1 is here, point 2 is here, point 3 is here, point 4 is here, which is not an efficient way for us to describe these large data sets. However, our intuition for what these statistics may mean is somewhat limited. And so, let me share with you a little bit of a starting point for an intuition of what these are. We know from a calculation perspective how to compute the mean. This is something that we do all the time. And so if we have a bunch of data sets, we say we just sum up all the values, we figure out how many total values are, and we divide it by the number of total values, and that gives us the mean. And you can see two parallel computations for the mean, one directly using the .mean API and one computed manually. If we want to compute the variance, we may or may not remember how we go about computing the variance. And when we compute the variance, what we're going to do is we're going to take each value and we're going to look at how far away it is from the mean. So we'll take each value and we'll subtract the mean from it. And because we want some notion of the magnitude of this distance, so that we want it to be the case that large magnitude of distance counts, but that if you have a positive distance and a negative distance that are symmetrical, they don't count. They don't negate each other. What we'll do is we'll square this. And then we'll sum this up and we'll divide this by the total number of values, and this computes the variance for us. And if we took a look at these two parallel computations of their variance, we'll see broadly the same answer. However, here's and let's also grab this down here. Just make sure we can view this. Perfect. Now, if we take a look at this formulation, we might notice that we're doing a sum and a length. So we could think of the variance as a sort of mean. We're meaning the average distance meaning to get the average distance from the central point, where we're looking at that distance squared. And one thing that pops up kind of interesting is, if we were to take a look at the units, if this were a physical quantity like heights or distances, something that we had measured, we're going to take a look at the units here. Clearly, the units of the underlying data is meters. So we could say, oh, the mean is 4.95. The data is centered around 4.95 meters. If we were to take a look at the variance, one of the unfortunate things about the variance is the units are kind of dodgy. It's meters squared. And if we're thinking about a linear measurement, and we're saying, oh, the variance is a summary statistic for this linear measurement, but it's in area terms, that becomes a little bit tricky for us to understand. And so this leads us to an intuition for why we might want the standard deviation. The standard deviation is merely, let's take the variance and let's just take the square root of the variance. And when we take the square root of the variance, we get more reasonable units. We can say, well, some notion of the distance from that mean is 0.98 meters. And here we can see a very simple intuition for the standard deviation. The standard deviation and the variance are computing for us what's the spread of the distribution. Is it clustered around the mean, or is it really far away from the mean? And this starts to give us a little bit more information about where that data set looks. And so if we give somebody both the mean and the standard deviation, they broadly know, okay, the average value is about here, and most values are very close to that, or most values are very spread out. Because the variance is computing what is this distance from this mean, the standard deviation is just giving that to you in more reasonable units. Now, there is another formulation for the variance that we won't get into, that we may get into if we do talk about expectations and probabilities a little bit more. But there's a second formulation for the variance here, where we're looking at the squared values and the mean of the squared values minus the square of the mean of the values, although I don't know that gives us a particular intuition at this particular point. We're not quite ready to get a good intuition for what the skew and the kurtosis are, but what I want to show you is mechanically what's going on with the skew and the kurtosis. The skew is what happens when, or is computed when, we try and figure out what the distance from the mean is. We divide that distance from the mean by the standard deviation. So we say, what is the number of standard deviations you are from the mean? We raise that to the third power, and we get the average of that. And one interesting thing you can see here is the skew is dimensionless. It doesn't have units. It's a ratio. It's a ratio of how many standard deviations the average value is from the mean raised to this third power. And this third power, what does that even really kind of mean? That's a little bit dodgy. If we think about what the kurtosis is about, it's a very similar formulation to the skew, but we're raising to the fourth power. And if we're not sure why we're raising to the third power, I'm pretty certain it's going to be a little bit tricky for us to understand why we might raise to the fourth power, but we will provide you an intuition in just a moment. I want to bring all of these definitions together to show you a little bit of terminology that will come up a couple of times and will come up every time you talk about these summary statistics. We can talk about the kurtosis, the skew, the variance, and the mean in terms of things like moments, raw moments, central moments, standardized moments. And so here we can see this is our computation for the kurtosis, and the computation for the skew is the exact same computation, except instead of the fourth power, it's the third power. We can see that the variance is part of this computation. We didn't divide by the standard deviation, and we raised everything to the second power. And you can think that here, and by the way, this is mislabeled, you can think here that the mean is another portion of this computation, but it's removing the subtraction of the mean here, and it's raising everything to the first power. One thing that we can say is that the mean, the variance, the skew, and the kurtosis are all summary statistics that represent moments and different powers of moments. The first moment, the second moment, the third, and the fourth moment. The first moment being a raw moment, meaning we're not demeaning it because that wouldn't be particularly meaningful. The second moment, the variance, being a central moment, we're demeaning it. We're trying to figure out how you are rotating around something at some central point, or how you are located around some central point, I should say. The skew and the kurtosis being standardized central moments. So we figure out how you are distributed around a central point, and then we standardize it to figure out that spread in terms of a number of standard deviations. And you can see this gives us a little bit of a sense for these. If we're to go back to our description, I want to just make sure that we see how this terminology lines up, because I find that the terminology, when you're seeing it for the first time, can be very confusing. We talk about the mean as a raw moment. We can talk about a moment around zero, which would just be every value and its distance from zero and the mean of that. We could talk about the moment around the mean, and we can think that the mean is the first moment around the mean, the first moment around zero. We can talk about an nth moment around the mean, and this is what we're talking about largely when we're talking about the skew and the kurtosis, minus this discussion of the standardization. The variance we can talk about as being the second moment around the mean. It's the squared distance from the mean and the mean of that. The standard deviation we can talk about as the square root of that second moment around the mean. And these standardized moments we can talk about as dividing by the standard deviation as part of our formulation. And so one thing that'll come up a little bit later is the first standard central moment of any distribution is always zero. The second standard central moment of any distribution is always one. It does not matter what the data looks like. And this is just a consequence of these formulations and a consequence of how we're presenting this vocabulary. And we can see this if we look at an actual data set and we compute these. It doesn't matter what this data set is. It doesn't matter what's contained within. These will always be 0 and 1. And the reason for that is, and this is why when we talk about the mean, we're talking about not a standardized central moment. It wouldn't be very useful. When we talk about the variance, we don't talk about a standardized central moment. It wouldn't be particularly useful because it would always be 0 or 1. And this is why you see that asymmetry before, because as a consequence of the formulation, it's not particularly useful to talk about standardized central first and second moments. It is interesting to talk about non-standardized central moments, non-standardized second central moments, and raw first moments. And I put a little bit of the algebra here, but we won't go through it in too much depth. It's in the notes for you to review. Now, I've said the word moment many times, and I want to give you an intuition for what all of this really means. If you learn the term moment in the field of physics, you'll learn it in terms of some measurement, some calculation that is a product of a distance and some measurement of a physical quantity. And the idea here is we're trying to give a sense for how these things are located or distributed in space. And so we can think about something like the center of mass. When we did our last physics class, we remember that we can model things as points, point masses at the center of mass. And so we have all sorts of weights orientated around in space, and we want to figure out, well, where is that center of mass? Where is the average point where we can see the representative mass of this object is? And this is what our first raw moment is. This is what the mean is. Mean is a measure of our center of mass. It's a physical quantity. When we talk about this from a physical perspective, we can also talk about what the rotational inertia of a piece of a physical entity is. You can think that if the mean is where all those weights are located and where the average point where those weights are located in space, you can think that if we have a bunch of points out to the edges, well, that's going to make it easier or harder for us to rotate this thing. Think about it. If you have a bunch of things clustered toward the center, you can spin it really fast, and it doesn't provide a lot of inertia against that desire to cause it to spin. But if you have them really spread out, then it has a particular rotational inertia. And you can imagine that it makes it a lot harder for you to move this thing rotationally. Well, it turns out that rotational inertia is actually the same thing as your variance. It is your second central standard moment. In statistics, instead of talking about this in terms of these product of distances and measurement, because we want to talk about these higher order moments, what we're talking about is a quantitative measure related to the shape of the graph of the values. So anytime we're computing a mean, a variance, a standard deviation, a skew, or a kurtosis, what we're really trying to communicate to somebody is, I don't want to tell you every single point in this data set, but I want to tell you broadly how it's shaped. I want to tell you broadly where that center of mass is. I want to tell you broadly what the spread of this is. That would be the mean and the variance, or the mean and the standard deviation. And I want to tell you how the tails look. And I want to tell you how this thing leans.